Alright, so I have to do this a bit separate here. Too pure for regular mortals, I guess, Bill Gates. But you get these two banging at it with both running the 555 chip, and I'll line that up so they'll start like this. But you need this three-phase motor kind of thing, and this happens out here at Delport sometimes. I start? Yeah, we're good.
Hello class, welcome back to another Learning Glass lecture on physics. We're talking about electric fields today, and we touched a little bit on this last time, but let's review just a little bit.
Well, but we're here for psychology, an electric field? Because you're probably with me and we don't have a breadboard, and
so
what we do have is paper and pencil, right? What we do got is this
and
E.
the electric
Ray.
field
He's
is
an electric guy.
As the force that a
and that's the B field in that,
see,
which he's going to be talking in
divided by the charge
and
of that test particle.
voltages and amps. And,
what does that mean? Well, let's say we have a big positive charge.
VIR, because that's your infrared. Then you got V. Okay.
That positive charge is going to exert an influence on a test charge. If this happens to be a positive
VR, and
charge, then we know what's going to happen, right? We talked about
and
what
I like
happens
to talk about that, like, again, it's
of the same sign. We said that
infrared,
likes repel.
And I like to make a video camera about it, and then we will have an interview about that video report, and that'll help you deal with
those two positive charges are going to separate.
I think it's resistance and current,
but let's say
or something
we don't
to that
have
effect,
any
right?
charge there.
Because that's essentially what they're doing.
We just erase
like charges like to repel themselves when you get too close together, because there's not a true fundamental that does it correctly. There's the geometric special relativity way, and then there's this semi-imperial mass
and that charge
variance of it that has
Q.
EM fields in it, right? Like it works like that. I know, like he's starting to slip into the E field if alphabetically. That was lined up in such a way, but the reality is gravity determines the order, not alphabetically. But you will need to know the alphabetical, figuring it out to get some puzzle pieces together in order to get all the edges in such a way that'll help you do that process. Now, is that the only way that things happen?
In this case, we know that it will experience a force.
It's not going to electricity other ways.
And the electric field is apparently F over Q naught. But we know what F is. F is Coulomb's law.
It's K over Q1, Q2
K, Q
over
Q
radius squared. Oh, I thought,
divided by R squared.
That is kind of Q1 and Q2.
We're going to divide that whole thing by Q naught.
Okay, so it's a partial derivative.
And there is a particular direction associated with this. Okay.
Right, so you are definitely into electricity, into a wire. And that thing's starting to split into temperature, magnetism,
you have a point charge sitting at the origin. This is our XY coordinate system.
Which parts of the skid steer make heat and
R is
traction
along
bones
a
like
radius.
Aluminum
so R hat is a radial unit vector. It's pointing away from the origin in this case.
It's
it
actually
would be pointing
silver,
away
copper,
from
gold,
the charge.
I think, if I'm not mistaken.
Okay. We can cross out the Q naughts right away. And so this whole thing simplifies to the following.
If you do A, derivative,
R squared,
right, it would be derivative AU, right? Because you need A over its position in the field,
a point charge,
which gives me not just its electrical, because you're all crazy super monsters running a guy with an electric pan F
point charge
for the field. That's how you got to get the gold by any other means, and the super dredge does it the other way.
KQ over R squared, R hat.
Make it a little, you need to smooth that out a little bit,
R
boss.
hat is just the direction. It means pointing away from the point charge. All right. So let's draw some electric fields.
The photons that you put in during this version are you in the stone mill.
If
right, and I run a little loop in that stone mill all the time, and if you do it right, the overhead Ingling angle camera becomes the ray. No matter what we do in there, no matter what kind of, we can make a cake, we can do stone, make an impossible woodworking joint, a Lincoln's hammer.
The arrows indicate the direction of the electric field. The lines indicate
Feynman diagram kind of a
field,
thing,
the density
which
of those
I'm
lines
pretty sure he gets into it at some
strength.
point in time.
Where the lines are tight together,
but this is a different variant.
Strong.
We are
where they are spread out,
looking inside of a copper wire. We don't know the diameter. It's in zeniths.
Positive charges,
and it's a couple of zeniths.
Sources.
Well, not only is the diameter a piece of it that plays into the math, but so is the composition. You would think, well, Sarge, I could just know. Copper comes from green rocks.
Sinks.
E.
The lines look exactly the same, but what changes is the direction of
the manufacturing
arrow.
For a smooth wire, with or without insulation, and why that may be important when it comes to grounding, ripping one back down, or why it has to be that way, because it'll start a fire. Not just by virtue of the math explaining that, but when it goes back to look through, why does that keep catching on fire? It'll make sense about that charge ripping back down through the pipes.
Sources and sinks, right? The source is like your faucet in your bathroom. You turn on the faucet, water comes out. The sink is where it drains into. It's where it disappears from your bathroom.
And there's
sources and sinks.
And then there's the difference. So the first time you had to solder a pipe.
That's not too bad.
Right. Against the time you did it 20 times after you did that, there will be a field just for that, where you get a bit of a jump or a step, or
looks like this. It goes
and for whatever reason I can't have that for making this wire bust off and off, because I had to build it out to here, right?
Lines, they had better come
I don't have any of this, but
a continuous line.
I now would have to figure out why, through whatever congruency here, another configuration of this on a line, not on a breadboard.
Field.
And
lots of things in the universe are, of course, dipoles.
So
this becomes
again, you know, knowing it like this, they usually don't bring it up in electrical engineering in it. But I had a stone mill boss who used to ride around.
Let's say we have
good boss, good at the loader, good at the very good boss.
Positive charge sitting right there.
And you know, he said, you know, here I was a laborer in the stone mill picking rock. Not making too much, doing everything in the world, and he had studied electrical. He had a master's in electrical engineering. And here he was out in the woods doing a thing. So again, we never really talked about it, but we could understand in the field that that's something to it.
We know that. It's zero.
And
why is it zero?
We get into the schematics of the overheads. They work like QED, soft linear effect distribution theory, because that kind of way about it is really good to the brain. But here's what they're doing, and this is really condensed. Now, if you don't see this kind of stuff, or E in you'll see geometry, you'll see an arbitrage to it, but that's real complicated stuff. Again, you know.
So let's put our point of interest.
Not only was there the site, but there's also other sites. There's also taking that whole concept and going, here's the road into the company in the morning. You're pulling off the main road because there's transformer here about passing through that. Well, I'm just a car driving. That's universal speed limit.
It must be pointing in that direction. Let's call